We will now review some basic aspects of vectors and the operations that we can do with them. We can define a vector and we have to place it first in the space. And the first problem we have is to establish a set of coordinate systems. And on them, with them we can define and write any vector we want. If you have some difficulties considering vectors and space, you may just have a look to the room you are sitting, and for instance, if you want to locate the screen of your computer you are using now, just look in the room for a corner. And in this corner, you immediately will see there are 3 edges coming out of the corner. 2 on the floor and 1 going up to the ceiling. Those are the 3 axes you will have here. And to represent any point, for instance your computer screen, then you have to move along a certain distance one of those axes or edges, then perpendicular to another one, and then go up to your table and get the place you are. So in this case we are going to represent that point with those 3 coordinates. We will name x, y, z, and they are just plotted here. 2 on the horizontal plane, 1 in the vertical one. And this is all you need to represent any point in space. Now, there are also vectors. And a vector is just, in the simplest form, is just a segment that has a tail and a head. We normally represent vectors with arrows. And the length of the segment is the magnitude of the vector. Now, in this case, you will see that we not only have a number to define the magnitude, but also there's a direction where this vector is pointing. We could really draw this vector as pointing to any other place, any other point in the space. But let's stick with this vector. The first thing we can do with this vector is just to project it and translate it to the origin, to this point here. In this case, we have exactly a vector that is parallel to the previous one and is a replica of it. Now, to represent a vector, we need something more than what we have until now. And this is a set of 3 unit vectors. Here, the notation is going to be a hat to represent a vector whose magnitude is just 1 metric unit of the rule we have used on the axis. We have here the 3 axes, the 3 orthogonal axes, and we will be using this notation for the vector. With this help, we can really decompose this vector in 3 other vectors. And here is the way they are represented. The vector along the axis, this edge, another one along this axis, y, and the z. And to go from the point, the origin of the vector, to the tip, we can move along this axis, along this one, and this one. Those 3 numbers are called the components of the vector. And for them, we will be using this notation. A number that has a subindex x for the x component, y, and z. And all those 3 just define the vector. But we can do something else. Since we are talking about direction for the vector, we could also draw 3 angles, the ones that make this vector with the x-axis, y, and z. And we call them normally alpha, beta, gamma, we represent by these letters, and they are normally called the direction cosines, because they are related to the direction, and they define this direction. In this case, if we do this, the vector will be written in this way. First the magnitude, then you have the 3 direction cosines that are really defining the 3 components. And this is the basic tools we will be using to represent the vectors. Now, with the vectors, we can do different operations. The simplest one is just a scalar product. This is sometimes also called a dot product because of the way we represent it. Now, in the case we have here, we just represent two vectors, A, B, magnitude A and B, and they form a certain angle. Two vectors always define a plane. They are on a plane. And here you have an important parameter, the angle alpha. The scalar product is directly related to the projection of the B vector on the A, or could also be of A into B. You do this and you get the same thing. And the value for this product is just a number, which is just the magnitude of the two vectors times the cosinus of the angle. And you could invert the product that is represented in this case by this dot, and that's the reason for the second name of this product. And you will see that it's exactly the same to project this way or do it in this other way, projecting A onto B. Now, if you do the same thing for the three unit vectors, this is what you're going to find. When you just do the dot product of the vector times itself, you get 1, because they are unit vectors, and the angle they make is 0. So just apply the rule and you get this. The same for y and the same for c. But if you multiply x times y, then you get 0, because the angle is 90 degrees. yc and cx. They are, in this sense, just an application of the rule. In general, you have two vectors, one with components ax, y, and c, the other with b, x, y, c. You just have this product. And if you expand this thing, you just break the brackets, then you will get 9 terms, and you apply the rule, and at the end you get this, which is the product of the x, y, and c components. And this is just a number, and this is why this is called a scalar product. There's a different product, and this is called a vector or cross product. In this case, we have the same vectors, the same angle, they represent the same thing, but the resulting operation is going to be different. Instead of getting a number in a scalar, we are going to get a vector. And this vector is going to be perpendicular to both and follow the right-hand rule. The right-hand rule means that if with your fingers move from A to B in this direction, the vector will point as your thumb is showing. And this is just the notation for this product. You get a product in this way. If you invert in this case, then you will get a different thing. So you have to be very careful with the way you note the vectors. So you just, in this way, you go through a right-hand operation going from A to B to get C. This is really what you get in there. But be very careful, because if you go the other way, if you go from B to A, this vector is not going to point in this direction, it's going to point in the opposite direction. And the magnitude of this product is going to be the product of the magnitude of both times, in this case, the sinus of the angle. So it's a different product, not only because of the numbers you get, but also because in this case, the result is a vector. When you apply this to any general vector, then first you have to work with the unit vectors. And in this case, the rule is different. If you multiply the vector by itself, you get 0. And if you multiply it in a right-hand way, those unit vectors, you get 1. If you invert any one of them, you will get -1. So remember this. This is the way we go from x to y, we get c, from y to c, we get x, and from c to x, we get y. And this is just the rule for those unit vectors. In general, when you write the vectors and you use this rule, you get a more complicated result than in the scalar case, and could be easily represented with the matrix notation. On the first row, you have the unit vectors. On the second, in this case, you have the A components, and you have the V components. And you expand them, and at the end, you will get that the vector has those three components related to the vector components by this rule. You can apply this in very general situations, but this is just the basic knowledge that we will be needing for dealing with our vector problems in this unit.